Hi, hello, how are you? Craig Chapman here with part 4 of your video series on experimenting with neural network simulation. Now I know that in the previous part I said that we were going to have a part 3.5 before we got to part 4, but I've changed my mind yet again. Having now returned home from my vacation, I find that my recording time is a little more limited, so I decided to reorder them once more. So in this part I am going to show you how backpropagation works. We won't be doing any coding at all in this part, it's simply a walk through the math, and in the next part we'll implement this in code, and then finally we'll look at what can be done to parallelize the implementation in a subsequent video. So I'm going to do things a little bit differently in this video than is typically done when teaching backpropagation. There are many sources of information on how backpropagation works online, and they cover the math in far more concise detail than I can. So a great example of this is the blog post that we looked at last week by Matt Mazur. If you want to understand the math behind backpropagation and gradient descent, I highly recommend reading this very well written post. So big thank you to Matt for writing this. Instead of covering this myself, I'm going to try and explain backpropagation without even mentioning the C word, calculus. I know, crazy, right? So what you'll learn from me instead of the detail of how backpropagation works is a higher level overview, and you'll also be provided with some formulae or formulas that work. So my hope is that in a relatively short video I can give you the knowledge to implement backpropagation and at least a vague understanding of how it works. I'll be keeping my example network the same as the one in Matt's blog post, so for the most part you should be able to refer back to the blog post for an understanding of how the math works. So we'll be keeping the same numbers and using the blog post to verify our results. So with all that said, we need to start by defining some simple terminology. Because our neurons are using the sigmoid function to squash their output into a range of 0 to 1, what we need is a way of describing that range, and we'll describe that range as the net, or the net range. So the net would be a value of 1, the net range being 0 to 1. A delta is simply the difference between two values. So for example, the delta of 3 and 1 is 2. 3 less 1 is 2. So therefore the net delta is the difference between 1 and some other value. For example, the net delta of 0.25 is 1 less 0.25, which gives us 0.75. So with those definitions in mind, let's get started. This is the neural network that we developed last week based on the blog post from Matt Mazur, which we're now using to verify our calculations. We input the values of 0.05 and 0.1 at the inputs, and with some preset weights we got the expected outputs of 0.7513 and 0.7729. Our target outputs for this training example are 0.01 and 0.99. So we need to adjust the weights of the network such that we move closer to these outputs. But there is a problem. At this point we could simply find the weighting values which are required to give us a precise output of 0.01 and 0.99. However, if we did this, then our network would only be good for this one calculation. So suppose this were the second set of inputs and the target outputs that we were presenting to train our network with. If we adjust the network to be precise for this set of data, we'd be overwriting the weights adjusted for the previous set of training data. Essentially our network would not learn, it would simply be the adjusted network to work for whichever was the last set of data we presented to it. So what we need is a way to adjust the network weights in the direction of the correct output, but by some small amount, so that as it learns it approaches the correct outputs for each piece of data in its training set. We achieve this by calculating what we call the error delta, that is the amount by which our results are incorrect with respect to their targets. So since we don't want to train our network to be entirely precise for this one training case, we use a fractional part of the error delta as determined by a parameter called the learning rate, which we'll introduce shortly. We can then calculate the amount to which each neuron contributes to the output, and we distribute the error across the weights according to their contribution. For example, if one weight, say weight 1, was contributing to the output 1 by 60%, then it would get an adjustment of 60% of the error amount after it's adjusted for the learning rate. In doing so, we nudge weight 1 towards the correct output. So let's begin by looking at how we calculate the error delta. We start by simply subtracting the output that we got from our network, output 1, from the target 1 for output 1. So this gives us our first delta value. We have target 1 less output 1. We repeat this step for the second output using the second target value. And now because we need some small amount of the error value, we square the result for the output 1, and we introduce our learning rate parameter, in this case 0.5, and multiply the error value by the learning rate. We repeat this process for output 2 using delta 2, and finally we sum the two error values to give us the total error amount for our network. Now that we have this information, we can begin calculating the weight adjustments for the synapses which contribute to the output layer. So we'll start with weight 5 as it contributes to output 1. The amount that we'll adjust W5, that is the delta for weight 5, dW5, is calculated by multiplying the output delta 1, because W5 contributes to output 1, by the net delta of output 1, which is output 1 multiplied by 1 less output 1, then by the value that we got from the hidden layer neuron in H1. So let's plug in those numbers, and our result for delta weight 5 is 0.08216704. So we repeat this step now for delta weight 6, this time using hidden neuron H2 in place of H1, because weight 6 connects hidden layer H2 to the output. We'll do the same calculation again for weight 7 this time, using the error delta 2 because that's the delta for output 2, but returning to hidden layer H1. And now, one more time, we'll repeat the calculation for weight 8 using delta 2 and output 2, but remaining on hidden layer H2. So we can now calculate the new value for weight 5 by subtracting the delta weight 5, dW5, multiplied by the learning rate from the previous value of W5. Repeat this for W6, and for W7, and finally for W8. So we now have some new values for our weights W5 through W8. So with new values calculated for the synapses leading to the output layer, it's now time to calculate the weights for the synapses leading to the hidden layer. Now this calculation is a little more involved than those for the output layer, because the output layer is a special case. It's so close to the outputs that calculating its effect on the outputs is easier. Calculating the effect of weights 1 through 4 on the outputs is more involved, because we have to take into account the amount to which hidden neurons H1 and H2 contribute to the output via weights 5 through 8. So we're going to remain focused on a 3-layer perceptron for these calculations, but you should keep in mind that the same effect on weights propagates back through the layers in deeper networks as well. So the amount that the weights contribute to the output, and therefore the amount of error for which they should be adjusted, diminishes as we propagate back through the network. This actually leads to a famous problem in training neural networks known as the vanishing gradient. I recommend reading up on this problem and its potential solutions as you develop more advanced neural network simulations. So the first thing we need to do is calculate the net delta of output 1 and multiply that by output 1. We then repeat this for output 2 to get the net delta of output 2. We can now use those net values to calculate the delta error which we're going to propagate back. So for output 1 we have the delta error that we calculated earlier multiplied by our net delta error, giving us delta error 1 or DE1. And the same is repeated for output 2, giving us delta error 2, DE2. We now calculate how much hidden layer neuron H1 affects output 1 of our network, which it does through W5. So we have DH11 equal to the weight of W5 multiplied by the net delta 1. We repeat this to find how hidden layer 1 affects output 2 through weight 7. So we're using our net delta 2 because this is output 2. So we now move on to hidden layer neuron H2 and how it affects our output through W6, and using our net delta N1 for output 1. And we do this calculation once more for the hidden layer neuron 2, H2, through the weight of W8 for output 2, using net delta n2. So we're now able to calculate the total amount of the error of our network, which should be attributed to hidden layer neuron H1 by the sum of DH11 and DH12. So this is error for H1. And we can do the same calculation for error of H2 for hidden layer neuron 2 by the sum of delta H21 and delta H22. So we're almost there. We just need to distribute each of these values across their input synaptic weights and we're home and dry. So we get our adjustment for weight 1, or delta weight 1, dW1, by multiplying input 1 by our error delta for hidden neuron H1, and then by multiplying all of that by H1 multiplied by the net delta of H1. We repeat this calculation using input I2 and we get the adjustment for weight 2. Repeat the calculation again for input 1 and our error delta for hidden layer neuron H2 and we get the adjustment delta for weight 3. And one more time using the error delta for hidden neuron H2 and input I2, we get our delta for weight 4. So now we have all of the adjustments we need to update the synaptic weights leading to the hidden layer. And if we bring back our calculations from earlier, we have the adjustments for the weights between the hidden layer and the output layer as well. So we'll bring back our total error calculation from earlier, 0.29837110876. And this was the total error of our network for inputs 0.05 and 0.1 before we adjusted the weights. So let's now adjust the weights and see what we get as outputs. With the new weights plugged in, we still don't have anything close to the target output values of 0.01 and 0.99. However, each of the values is very slightly closer to those targets, and so the total error calculation shows that our error has reduced by 0.00734333,469. Over thousands of iterations of this algorithm, the output of our network should approach an error of 0, although it may never reach 0, and that's an important thing to realize about neural network simulations. They'll never, or rather they ought never, produce a 100% accurate result with no error. Instead, through training, they come closer and closer to an approximation of the desired output. So by altering the training inputs and target outputs during the training, the network can become useful for providing approximately the correct output for whichever problem it's being trained. Or rather, as I like to say it, they can give an answer with a degree of certainty, but they're never entirely certain. The smaller the error, the closer to certain they are. So keep this in mind when you purchase your next self-driving car, please, won't you? Now, if for a change I'm able to keep my schedule, in the next video we'll look at implementing the backpropagation algorithm in our neural network simulation. Until then, my name is Craig Chapman, and thanks for watching.